All right, ready to dive deep into the atom?
Yeah, let's do it.
I'm ready.
Cool.
So we all know the basics, right?
Uh,
Nucleus with electrons spinning around it.
yeah.
But the journey to figuring all that out,
Oh, yeah.
oh, it's a wild one.
It's a wild ride.
So before we knew all that, before the model we all know and love, what was the prevailing theory?
So before Rutherford's experiment, the prevailing theory was what's called the plum pudding model.
Plum pudding.
Plum pudding.
Really?
Yeah.
So I'm more of a chocolate cake person myself, but all right.
Yeah, well, this is
I guess plum pudding works too.
it's named that because, if you can imagine a Christmas pudding with raisins scattered throughout, the plum pudding model essentially saw the atom as a big positively charged sphere
Okay.
with negatively charged electrons studded within it, kind of like those plums in a pudding.
So just to be clear, we're talking about like a diffuse cloud of positive charge
Exactly.
with these tiny little electrons just hanging out in there.
Yeah, like plums in a pudding.
Okay, I'm trying to picture this. It's like, how do those electrons even stay put in all that positive goo?
Right.
Wouldn't they just get, I don't know, repelled or something?
Yeah, you'd think so, right. And, even back then, not everyone was on board with this whole plum pudding idea.
Oh, really?
Yeah, there were some skeptics.
Okay, tell me more.
There was this Japanese physicist named Hantaro Nagaoka.
Oh, okay.
He actually proposed a model where the electrons orbited the positive charge, kind of like the rings around Saturn.
So even before Rutherford's big experiment, there were already some alternative ideas floating around.
Exactly.
It wasn't just all plum pudding and everyone agreeing, huh?
Science is rarely ever that simple.
Okay, I love that.
Yeah.
It's a good reminder that science is messy.
It is.
It's always evolving.
Yeah.
So speaking of, let's talk about the experiment that really shook things up. The one that basically blew the plum pudding model out of the water.
Right. The Rutherford gold foil experiment.
Right.
You've probably heard of it.
The one in all the textbooks. Okay, for those who maybe haven't or need a refresher, break it down for us. What was it all about?
So picture this. You have a thin sheet of gold foil,
Like super thin, right?
thinner than a piece of paper.
Okay.
And they're bombarding this foil with these things called alpha particles.
Alpha particles.
Yeah.
Those are like,
They're positively charged particles.
okay, so tiny little bullets of positive charge.
Exactly.
Okay.
And they're firing them at this gold foil.
I'm trying to picture this. So you've got these little bullets of positive charge.
Yeah.
They're shooting them at this really thin piece of gold.
Yeah.
What were they expecting to see?
Well, based on the plum pudding model,
Right.
they thought, the alpha particles would just kind of sail straight through
So like right through the pudding.
with maybe a little bit of deflection, but nothing major,
Okay.
because they figured the positive charge was just spread out evenly in the atom.
Wait, so they were expecting these positively charged particles
Yeah.
to just pass through this positively charged pudding
Pretty much.
without much fuss?
Yeah, the thought was that the positive charge was so diffuse that it wouldn't offer much resistance.
Something tells me it didn't quite go as planned.
You would be correct.
Okay, lay it on me.
All right, so here's what happened.
Yeah.
Most of the alpha particles, they went straight through like they expected.
Okay.
But here's the thing.
Yeah.
A small percentage of them were deflected at these crazy angles.
Oh, hold on.
Some even bounced straight back.
Seriously.
It was like those tiny bullets ricocheting off tissue paper.
That's insane. So what happened? Did the scientists just scratch their heads and say, well, that's weird?
Well, at first, they were definitely puzzled.
Yeah.
This result completely contradicted the plum pudding model.
Right, because if the positive charge was really spread out evenly, those alpha particles shouldn't have been deflected like that.
Exactly.
So what did they conclude?
Well, Rutherford, who was leading this experiment, he realized that this meant the atom couldn't be this big, diffuse, pudding-like thing.
Okay.
There had to be something else going on. There had to
Yeah.
be something much smaller, much denser, and much more concentrated in terms of positive charge.
Enter the nucleus.
Exactly.
So this is where the idea of a nucleus at the center of the atom comes into play, right?
Absolutely.
The thing that was causing those wild deflections in the alpha particles.
It's like a tiny supercharged bowling ball in a giant empty bowling alley.
Okay, I love that analogy.
And then, of course, he proposed that the negatively charged electrons were orbiting this nucleus at a distance, much like planets around the sun.
So thanks to this one crazy experiment, The whole picture of the atom got flipped on its head.
Completely revolutionized.
We went from plum pudding to a mini solar system.
Quite the makeover, right?
It makes you wonder, though, what else about the atom
Yeah,
did they maybe get wrong that we now just take for granted?
that's a great question, and it really highlights the constantly evolving nature of science.
Yeah.
Even Rutherford's model, as groundbreaking as it was, wasn't the final word on the atom.
It wasn't.
Nope, there were still some mysteries lurking.
Oh, I knew there had to be more.
Puzzles even this model couldn't solve.
Okay, before we dive into those mysteries, which I am dying to hear about, let's just pause for a second and appreciate what Rutherford and his team accomplished.
Wow.
I mean, figuring all this out back then with the limited technology they had, it's just mind-blowing.
It really is a testament to the power of human ingenuity.
Absolutely.
And you know what's really cool?
Yeah.
There's this computer model out there that lets you visualize all this, the different atomic models,
Wait, seriously?
the gold foil experiment, you name it.
You can actually see these atoms and experiments in action.
You got it?
Oh, man, I gotta check that out. It's one thing to hear about all this, but to actually see it?
It brings it to life, right?
Yeah, that's next level understanding. Okay, well, back to those mysteries you teased. You mentioned Rutherford's model wasn't perfect.
Right.
What were the problems with it? What didn't it explain?
So one big issue was that, according to classical physics, those electrons orbiting the nucleus should be losing energy
Losing energy.
and essentially spiraling inwards towards the nucleus.
Wait, so the atom should be, like, collapsing in on itself all the time?
You would think, right?
That doesn't sound very stable.
Luckily, reality doesn't always follow the rules of classical physics.
Okay, that's good to hear.
Yeah.
So what was the missing piece?
What saved the atom from imploding?
Yes, what saved the atom?
Well, it took a revolutionary new theory to explain it.
Okay, hit me with it.
Quantum mechanics.
Quantum mechanics. Okay, now we're getting into the really weird stuff.
Yeah, it's a whole other level.
It's one of those things I've heard of, but it always sounded so intimidating.
It definitely challenges our everyday understanding of how things work.
So what does quantum mechanics say about the atom? Does it still have a nucleus?
It does.
Okay.
It still has a nucleus.
Okay.
But the electrons, they don't actually orbit in these neat little circles like planets.
I don't.
Instead,
They...
they exist in these fuzzy, probability-driven clouds called orbitals.
Wait, hold on. Probability-driven clouds? Are you telling me we don't actually know exactly where an electron is at any given moment?
That's exactly what I'm saying.
Wow. Okay, my brain is officially melting.
Yeah, it's a whole different way of thinking about the atom.
So instead of this neat and tidy solar system, we have this blurry, uncertain quantum world.
In a way, yes.
Okay, so quantum mechanics basically said, forget those nice, neat orbits. Electrons play by a different set of rules.
Pretty much.
And those rules, as strange as they may seem, they govern, like, everything in the universe.
That's the crazy thing, yeah.
From the smallest atom to the biggest star.
It's mind-boggling, but also kind of beautiful.
Okay, well, I think we need a minute to process all that. We've gone from plum pudding to a miniature solar system to the mind-bending world of quantum mechanics, all to understand this tiny little particle. I'm exhausted, but completely fascinated.
I know, right?
So what happens next in this atomic adventure? Where do we go from here?
Well, the story of the atom doesn't end with theory.
It doesn't.
No way. It has real-world applications that touch every aspect of our lives.
Okay, you've got my attention. Tell me, how has this tiny particle made such a big impact?
Think about it. Medicine, technology, even archaeology, they've all been transformed by our understanding of the atom.
Okay, I'm ready for part 2 of this atomic adventure. This is getting good.
It is, isn't it?
All right, let's take a quick break and we'll be right back with more mind-blowing atomic insights.
See you in a bit. So we've talked about how atoms are mostly empty space.
Yeah, it's a bit of a head scratcher, right?
Okay.
I mean, if everything's made of atoms and atoms are mostly empty space,
Uh-huh.
why don't we just, like, fall through things?
That's a great question.
Or walk through walls?
Yeah.
It doesn't really make sense, does it?
It's one of those things where our everyday experience kind of clashes with the science.
Right, exactly.
But there's a reason for that. And it all boils down to the forces at play inside the atom.
Forces.
Yeah, specifically the electromagnetic force.
Okay, I'm listening.
So even though there's a lot of empty space,
Mm-hmm.
those electrons whizzing around the nucleus, they create a pretty powerful force field.
A force field.
Yeah.
Okay, now you're making it sound like Star Wars or something.
It's not quite lasers and spaceships, but it's kind of similar in a way.
Okay, how so?
Think about magnets, right? You know, the two magnets can repel each other without actually touching?
Yeah, they kind of push each other away,
Exactly.
even if they're not, like, physically in contact.
That's the electromagnetic force in action.
Oh, I
And
see.
it's the same principle at work with atoms.
So even though atoms are mostly empty space, those force fields created by the electrons, they're kind of like invisible barriers that stop atoms from just passing through each other.
Exactly. It's like each atom has its own little force field bubble.
Okay, so it's not the stuff inside the atom that makes matter feel solid,
Mm-hmm.
but the forces between them.
It's all about those interactions.
That's pretty wild when you think about it.
It is. It changes how we think about what solid really means.
It really does.
And it gets even more fascinating when you start to think about how the arrangement of those electrons,
Yeah.
like their energy levels and how they interact,
Mm-hmm.
that determines the properties of an element.
Wait, what do you mean?
So the way those electrons are arranged,
Mm.
that dictates whether something's a metal or a gas or a liquid. Yeah, it's like
Okay.
each atom has its own personality,
Okay.
and that personality is determined by how its electrons are arranged.
So basically, everything in the universe, from the air we breathe to the mountains we climb,
Mhm.
it all boils down to how those tiny electrons are arranged within atoms.
It's pretty amazing, right?
It is. It's like this incredible symphony of tiny particles all working together to create the world we see.
And it all started with that one simple experiment, shooting those alpha particles at that gold foil.
Right, Rutherford's experiment.
Who would have thought those tiny deflections would unlock such a profound understanding of the universe?
And you mentioned earlier that Rutherford's model wasn't the complete picture, right? That there were still some things it couldn't explain.
There were still some mysteries to solve.
Okay, like what
Right.
didn't Rutherford's model account for?
Well, one of the biggest issues was that, according to classical physics,
Okay.
those electrons orbiting the nucleus should be losing energy
Losing energy.
and spiraling inwards towards the nucleus.
So like the atom should be constantly collapsing.
You would think so, right?
Boy, that doesn't sound good.
Thankfully, things don't work exactly like that.
Okay, good.
The universe had other plans.
So what was the saving grace? What stopped those atoms from imploding?
It took a whole new theory to explain it. Quantum mechanics.
Quantum mechanics.
Yeah.
All right, now we're talking.
This is where things get really interesting.
I know, I'm a little nervous but excited.
Quantum mechanics is a bit of a mind bender.
So quantum mechanics, this is where the electrons don't actually orbit the nucleus in neat little circles.
Right, it's not like a tiny solar system anymore.
Okay, so what's the new picture? How do electrons behave according to quantum mechanics?
Well, the idea is that electrons exist in these fuzzy, probability-driven clouds called orbitals.
Probability-driven clouds.
Yeah,
So we don't actually know exactly where an electron is at any given moment.
exactly. It's all about probabilities.
Okay, so it's not like a neat and tidy solar system anymore.
Not quite.
It's more like, I don't know, a blurry, uncertain atomic world.
Yeah, that's a good way to put it.
All right, so quantum mechanics basically said, forget those nice, neat orbits. Electrons play by a different set of rules.
And those rules, as strange as they might seem, they govern the behavior of everything in the universe, from the smallest atom to the largest star.
It's amazing to think about.
It is. It's mind-blowing.
We've gone from plum pudding to a miniature solar system to the mind-bending world of quantum mechanics, all to understand this tiny little particle. I need a nap, but this is just too fascinating.
I know, right?
So where do we go from here? What's the next chapter in this atomic saga?
Well, understanding the atom isn't just about theoretical physics.
It isn't.
No way.
Yeah.
It has real-world implications.
Okay, I'm intrigued. Like, what? Give me some examples.
We're talking everything from medicine to technology to archaeology.
Okay, you officially have my attention. Tell me more about how this tiny particle has had such a big impact on our lives. All right, so we've gone on this incredible journey from plum pudding to miniature solar systems, even dipping our toes into the quantum realm.
Yeah, it's been quite the adventure.
It really has. But here's the thing that I find so fascinating. Understanding the atom, it's not just about some abstract scientific theory.
Right.
It's about real-world applications that affect every aspect of our lives.
Absolutely.
So let's talk about that. Give me some concrete examples. How has this tiny particle had such a massive impact?
Well, let's start with something I think we can all relate to. Medicine.
Okay, yeah, I'm with you.
Medical imaging, things like x-rays, MRI scans, PE scans, all these amazing tools that allow doctors to see inside the human body.
Yeah.
They all rely on our understanding of atomic structure.
Wow. So when I get an X-ray, they're basically shooting these high-energy photons at me.
Yeah,
And those photons are interacting with the atoms in my body to create an image.
exactly. And each type of imaging uses different properties of atoms and how they interact with energy to create those detailed pictures.
So it's like having a superpower, being able to see through flesh and bone.
It really is, all
Wow.
thanks to our understanding of the atom.
And what about technology? You mentioned that
Oh
earlier.
yeah, technology is a huge one. Think about all the digital devices we use every day, our smartphones, computers, tablet. They're all powered by semiconductors, which are materials that can control the flow of electricity. And guess what? Semiconductors rely on the precise arrangement of atoms to work their magic.
Hold on. So you're telling me the digital revolution, the entire information age, it's essentially built on our understanding of how electrons move and interact within atoms.
Pretty much, yeah.
That's just, wow, mind-blowing.
Those tiny particles, they're responsible for the vast networks of information we access every day.
And it doesn't stop there, right? I mean, even archaeologists use techniques like carbon dating, which relies on our knowledge of atomic decay.
Exactly. So we're talking about applications across a vast spectrum of human endeavor.
The atom is like this hidden key that unlocks so much potential in so many different fields.
It really is.
That's
And it
it.
just keeps going. In materials science, we're constantly manipulating atoms to create new materials with incredible properties.
Okay, give me some examples. What kind of incredible properties?
Things like super strong alloys used in aerospace, or flexible electronics that can bend and stretch. The possibilities are pretty much endless.
It sounds like science fiction becoming reality, and it all started with those early scientists, like grappling with the mysteries of this tiny invisible particle. It makes you wonder, what's next for atomic research?
Well, one exciting area is nanotechnology, which is
Hmm.
basically the ability to manipulate matter at the atomic and molecular level to create completely new materials and devices.
Nanotechnology. Okay, yeah, I've heard of that. So like building things atom by atom.
Exactly. Imagine tiny machines that can deliver drugs directly to cells or materials with unheard of strength and flexibility.
It's amazing to think about. It feels like we're entering this whole new era of scientific discovery.
We are, and it all goes back to that same sense of curiosity and wonder that drove those early pioneers of atomic theory.
That's such a great point. It's a reminder that the universe is full of mysteries and that even the smallest things can hold the greatest secrets. Well, we hope this deep dive has sparked your own curiosity about the atom and the incredible world that it unlocks. Keep exploring, keep questioning, and who knows, maybe you'll be the one to make the next groundbreaking discovery.
And remember, the next time you look at seemingly solid objects around you, take a moment to appreciate the incredible dance of atoms and forces that make it all possible. It's a truly amazing universe we live in.